Hypothalamus artificial intelligence, HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Presents the short conference, High Complexity Mathematical Modeling in the Industry 4.0 Era. Mathematical Programming: The Way to Artificial General Intelligence. Conference prepared and edited by Jesús Velásquez-Bermúdez. His resume may be found on LinkedIn. The new way of mathematics is directly related to the parallel thinking, and today it can be said that like paper-based math, sequential mathematics for single-processor computers, will be in the short term a dead language. As in the human brain, in the future only parallel mathematical thinking will be practical. The new analytics is autonomous, parallel, and distributed. Artificial neural nets. In 1943, Warren McCulloch and Walter Pitts created the concept of artificial neural networks. They published the article, A Logical Calculation of the Ideas Immanent in Nervous Activity. McCulloch and Pitts tried to explain how the brain could produce highly complex patterns, by using many basic cells that are connected. Neural networks were growing, and in practice they took the name of artificial intelligence. They were also called machine learning. Neural networks have grown without paying attention to the structure of the brain's architecture, that is, how the main parts of the brain are connected, the cerebral cortex, the hypothalamus and the hippocampus, and the functions they fulfill. Neural networks developed as the fundamental element of communications within the brain, but without consider how they were connected, a lost component's fundamentals. At first, artificial neural networks were very small and gradually became GPT, in the hope of reaching AGI, which could be associated with a very large artificial neural network representing the entire brain, associated with many models, also very large, that with an infinite number of parameters would represent all the connectivity of the brain, ignoring the smart architecture of the brain. Given this lack of structure, we have a sum of neural network models that produce a supermodel whose networks come together in the brain, as if it were a Lego game in a backpack. The growth of artificial neural networks is due to the great growth of computational power, and not to a change in paradigm, which after 80 years should have occurred. It is to be expected that before the end of the Industry 4.0 era this change will take place. Artificial brains is a disruptive modeling methodologies for Industry 4.0, based on the integration of artificial intelligence and mathematical programming. The science of decision-making using digital computers emerged in 1947 and can be attributed to George Dantzig. The AI in which artificial brains are located, HI calls it artificial intelligence for decision-making. Dantzig's work gave rise to mathematical programming. Although mathematical programming is clearly a way to provide artificial intelligence to computers, and it grew much faster than the so-called artificial intelligence based on neural networks, to date mathematical programming is considered by almost all users, and by many scientists, as a methodology that is not part of artificial intelligence. There is no awareness that it is necessary for humanity, since its function is to optimize decisions. Mathematical programming has benefited from computational power, but not as much as artificial neural networks. This is due to the investment that humanity has made in GPT models. This indicates that in a new era, its power will play out, as it is much closer to helping achieve artificial general intelligence, AGI, a hypothetical type of highly autonomous artificial intelligence, I, that would match or exceed human capabilities in most, or all, economically valuable cognitive work. Artificial brains is a disruptive modeling methodologies for Industry 4.0, based on the integration of artificial intelligence and mathematical programming. Artificial brains are an invention of HI, due to their expertise in complex modeling. The creator of the human brain conceived it as the integration of three main organs, or systems: neocortex, hypothalamus and hippocampus. The hypothalamus is part of the thalamus. McCulloch and Pitts theory has been around for more than 80 years. However, Velásquez-Bermúdez's work, spanning 35 years of research and technological development, has resulted in artificial brains, which are a new way of thinking about artificial intelligence. Artificial brains emulate the structure of the brain and use it to build the mathematical models. The structure of an artificial brain is made up of the artificial hypothalamus, hippocampus, and cortex, all of which perform functions like human equivalents. The connection between all the subsystems, within and between them, is made by bioneurons. For this, biological neural networks are formed, through which information flows in the brain, and in general in the human body. The neocortex contains millions of neurons that communicate with each other, to capture the world that occurs around the human being. The connectivity of these neurons does not occur based on a dense network, that connects all neurons to each other. Connectivity is based on a sparse network, which can be assimilated to a sparse array. Artificial brains come from neuroscientific studies. The construction of the artificial cortex determines the connectivity of the artificial neurons, which are associated with the atoms of the system. In mathematical models, it is common to use a matrix that establishes the relationship between columns with variables and equations with rows. These matrices are scattered. This is the basis of cortical modeling. Emphasizing that Hai is not an expert in neuroscience, its interpretation of the functioning of the brain is presented. The cerebral cortex stores all the connectivity of the neural networks that make up the brain. It is the map of the brain. The hypothalamus is a region of the brain that plays a crucial role in regulating essential bodily functions, including body temperature, hunger, thirst, sleep, mood, and hormone release. In addition, the hypothalamus helps maintain homeostasis, like the body's internal balance, through its connections with the autonomic nervous system and the endocrine system. It can be said that it is the motor of the brain. It is a vital structure for the harmonious functioning of the body, acting as a central control center for various physiological and behavioral functions. The hypothalamus is the organ that ensures the proper functioning of the human being. The connectivity of neurons in the cortex determines how the hypothalamus should function. The hippocampus. Storage structures and processes from the decision-making that must be faced permanently. The artificial hippocampus is based on the mathematical synthesis of the information generated by algorithms and problem-solving processes, to use it in new runs of these algorithms to speed up the problem solution in real time. Artificial hippocampus store, like in the humans, the experience, and the knowledge acquired over time. The hippocampus is responsible for managing memory, which interacts with the hypothalamus, to determine the actions that the human being will perform, that is, decisions. Artificial entrepreneurial brains are based on these hypotheses. Donald Oldingham is best known for his theory of Hebbian learning, which he introduced in his classic work The Organization of Behavior in 1949. Hebb has been described as the father of neuropsychology and neural networks. The central concept of Hebb's theory is summed up in the phrase, cells that fire together, wire together. According to this idea, when an A neuron is repeatedly involved in the activation of a B neuron, the synapses between them are strengthened. Hebb's theory has shown that learning does not increase the number of neurons, but it does increase the connectivity between them. This principle suggests that the concurrence of neural activity is the basis for learning and memory. Synaptic strengthening. When a presynaptic neuron and a postsynaptic neuron are activated simultaneously, the connections between them are strengthened. Activity-dependent plasticity. The efficiency of synaptic connections is not static but can be modified as a function of neuronal activity. This plasticity is essential for adaptive learning and memory. From the point of view of Hai, one part of the artificial hippocampus processes the information stored in the other part, to develop a learning process. Learning takes the form of the generation of new neural connections, which must be stored in the artificial cerebral cortex, to be used in the future by the artificial hypothalamus. This high vision of artificial intelligence, built from the workings of the human brain, is currently unique in the world. Hai is researching in Hai's algorithms learning as the next logical step to machine learning methods. Sparse analytics, or parallel and distributed analytics, is the methodological basis of artificial brains. Hai is the creator of the concept of artificial entrepreneurial brains, which is supported by the development of parallel thinking, when a complex system must be analyzed. The evolution of analytics, the mathematical science of analyzing and solving real-world problems, occurs in three directions: productivity or speed of the technologies, complexity of the problems it can solve, and parallel thinking. On the other hand, there are three factors that are evolving and that allow the growth of analytics. Computing, which has evolved from monolithic to distributed processing, through parallel and dispersed processes. Types of analysis, which are classified as descriptive, predictive, prescriptive and cognitive, and mathematics, level of knowledge used, algebra, artificial intelligence, stochastic and robust mathematical programming and artificial brains. To be in the state-of-the-art of analytics, you need to work in the top-level row. There are two approaches to process data from a super-measurement system that provides a non-enumerating amount of data, in real time and asynchronously, parallel analytics and distributed analytics. These two terms seem to be the same, but they are different and complementary terms. The parallelism and distribution of computing processing goes beyond the simple construction of parallel mathematical algorithms. It implies a way of facing problems with the bottom-up approach, from the description of atoms to integrating the vision of the entire system. It is a way of thinking about mathematics, according to the development of computer technologies. This is consistent with the abolition of monolithic computer applications, to make way for distributed applications based on microservices. Then the next step of advanced analytics is sparse analytics, which is based on parallel and distributed analytics. Asynchronous parallel analytics, called asynchronous parallel optimization by Velásquez, in 1995, 1997, and 1998, is defined as the act of solving a mathematical problem, using multiple cores on a computer, or on a computer grid, using modern multiprocessing environments, uniting the theories of decomposition and partition of large systems, that allow to structure complex multi-level mathematical models. Parallel analytics distributes workloads for data analysis, across multiple nodes in a server cluster, rather than addressing a large problem on a single supernode. The algorithms run on each node, processing a subset of the data. When processing is complete, or whenever required, datasets are aggregated, or rejoined, to generate collective information. There are many advantages of the asynchronous parallel approach. Less time to get information. By putting multiple nodes to work on the same problem, you can get insights from the data much more quickly than would be possible by running an analytics application on a single supernode with linear processing. This is a huge benefit when you want to get quick responses from massive amounts of data, and asynchronous processing allows to produce information that can be stored in memory until it is required by some subproblem. This speeds up the solution. In addition, it requires less demand for resources, avoiding congestion in computer systems. Distributed analytics is based on parallel analytics, and it is the distribution of the mathematical modeling process, in many agents that act simultaneous and independently, when they received information from its exogenous environment. The process can be summarized in the following steps. From a top-down process analysis, is possible to construct mathematical or logical rules of interaction between multiple agents, representing each one a part of the system. Jointly, all the agents can represent the state of the reality. Starting from math or logic rules, following an approach bottom-up, is possible to build segmented or atomized models of the real world. Using asynchronous parallel processing, it is possible to define the simultaneous actions of all agents that keep on the right path a cyber-physical system. This processing is different from the traditional one, based on the synchronized use of mathematical models that are executed periodically. Autonomous real-time distributed optimization. Mathematically, this process may be supported by large-scale optimization algorithms aimed at solving very large optimization mathematical problems, based on the intensive use of methodologies for partitioning and decomposition of systems. New technologies and big data shift from traditional optimization based on synchronized moments to modern optimization based on real-time events, in which models will run autonomously, when necessary, by events. Autonomous real-time distributed analytics is a topic open to researchers in advanced analytics. This evolution may be summarized as the shift from artificial intelligence to artificial general intelligence, that evolves from artificial intelligence very powerful in pattern recognition, to intelligence that powers the human brain, becoming an exobrain with high decision-making capacity, in real time, and autonomously. The decision support systems, DSS, were conceptualized as a set of mathematical models that exchange information between them, working offline. The artificial brain is the evolution of DSS under the Industry 4.0 revolution, that is conceptualized as a set of mathematical models that exchange autonomously information between them, working online, using distributed optimization. When all the models that make up a company are solved using the concepts of real-time distributed optimization, an artificial hypothalamus is obtained. This is how the human brain faces reality, using multiple models of reality, acting permanently in parallel, to make decisions. So, the artificial hypothalamus, a part of the artificial brain, is the algorithm that control the workflow of the models of the decision support system. It includes a general math language between algorithms that guarantees that the system is in the optimal path. This is based on the duality theory. In real-time and uncertain systems, the concept of an optimal point must be replaced by that of optimal path, as the one who is always close to the ideal optimal points. The algorithm that simulates the hypothalamus is assembled by Optex, the HI's artificial intelligence, to generate mathematical programming solutions, using the models that traditionally make up a decision support system. Artificial brains are backed by the technological capacity of computing. It is traditional to associate mathematical modeling with large-scale computing, which today is linked to cloud computing, integrated by supercomputers of bits, and by the birth of quantum computers, which are the beginning of a new era. The current state of the computer technologies involves the integration of edge computing and cloud computing to implement systems with multiple highly complex mathematical models that can be run in parallel. Finally, there are now in the world machines that think, that learn, and that create. Moreover, their ability to do these things is going to increase rapidly until, in the visible future, the range of problems they can handle will be coextensive with the range to which the human mind has been applied. In 1972. In the book Human Problem Solving, wrote by Alan Newell and Herbert Simon. Thank you very much for your attention.